Hello class, this is Mrs. Gallegos, and today's tutorial we will learn how to write an electron configuration. This is topic 2.2 in your textbook, pages 59 to 62. There is much theory behind writing electron configurations, but in this tutorial we'll just talk about writing the configuration itself. So there's three rules we need to follow when we write a configuration: the Aufbau principle, the Pauli exclusion principle, and Hund's rule. Aufbau principle tells us we always put the electrons in the lowest energy orbital that is available first. Then we move up to higher ones. The way that we can know which orbital has the lowest energy is by looking at this Aufbau diagram, and I'll show you how to use that in a minute. The Pauli exclusion principle tells us that when we have two electrons occupying the same orbital, they must be spinning in opposite directions. Because an electron is a charged particle that's spinning, there's a magnetic field set up. So if they're both spinning the same direction, they'll repel each other out of the orbital. So they must be in opposite spins. Hund's rule tells us that when we are filling different orbitals in a sublevel, for example, S, there's only one orbital, but in P, there are three orbitals. So when we're filling those three orbitals, first we fill them singly, then the orbitals can be occupied in pairs. It's often useful to think of electron configurations as a desk clerk filling floors in a hotel, where each floor is analogized with the principal quantum levels, and each room is an orbital. So the Aufbau hotel, following the rules of Aufbau, would always put its first customer in the first floor, which would be the least expensive or lowest energy room, and the first person would be occupying a bed going in one direction and another in the other direction. And this would be following our Pauli principle, where we have to have spin up and spin down. Then once we're done filling the first floor, then we go to the higher energy, higher floor, on the second floor. There I have two different types of rooms. I have a suite room and I have a penthouse. Well, since the suite room is lower energy, I'm going to fill it first. That's Aufbau principle, and again, one person with their head facing this way and one person with their head facing that way. Each orbital can have double occupancy. But once I fill the suite room in the second floor, I go to my next higher energy, or my more expensive room, which is a penthouse room. And I have three penthouse rooms. So first I'll put one person in each of my penthouse rooms, and then I'll do double occupancy again. Their bed is facing the other opposite direction to show our Pauli exclusion principle. And then I just showed Hund's rule because I put one person in each room and then I did double occupancy. Well, now the second floor is filled, so I'm forced to go to the third floor. Here my cheapest room is the suite room, and so I have double occupancy there before I go and I fill up my three penthouse rooms, single occupancy, and then double occupancy. Now here's an interesting thing. Because these deluxe rooms are so expensive, I'm going to go up to the fourth floor and fill up my suite room with two people, because it's actually less expensive even though it's on the fourth floor. Then I'm going to go back down to the third floor and fill up my 5 deluxe rooms, but first single occupancy and then double occupancy. And this is how I go ahead and fill the rooms in my Aufbau hotel with electron people. So there are three different types of electron configurations. The one that I just demonstrated with my Aufbau hotel analogy is called an orbital diagram. There we actually can see the electrons, which are symbolized by arrows going up and down to represent Pauli exclusion principle of opposite spins. The one that we're most familiar with is the full electron configuration. In this case, I don't see orbitals as boxes. I just see the name, the principal energy level, the type of sub-energy level or orbital, and then this superscript right here tells me how many electrons are in the orbital. So I could add that in here. I could say 1s has 2 electrons, 2s has 2 electrons, 2p has 6 electrons, and 3s has 2, and 3p just has 1. So this electron configuration is a shortcut. I could even go shorter, and I could replace all of this with the symbol of the electron, I could replace all of this, 1s2, 2s2, and 2p6, because that's the configuration of the noble gas neon, and then all I have to do is write the part of the configuration that's more electrons than neon, and this is called the condensed configuration. Let's practice. Alright, so let's draw the orbital diagram for chlorine. If I look up on my periodic table, I'll see that chlorine has 17 electrons. So, I'm going to, like Aufbau said, I'm going to start with my lowest energy orbital, and every orbital has 2 electrons in it. Then I go up 1 energy level to my second principal energy level, and there's an s orbital, so I fill that first, and then after that I fill the p orbitals first singly, according to Hund's rule, and then doubly, and opposite spins, according to Pauli exclusion principle. So I have 4 and 6 is 10, so I need 7 more. So I'm going to go up to the third energy level, and I put 2 electrons there. And then on my next energy level in the third, I'm going to fill up singly, according to Hund's rule, and then doubly my last 2 electrons. And here are my 17 electrons, and here's the orbital diagram for chlorine. The next kind of orbital diagram is electron configuration. And we're going to do the full electron configuration for manganese and the manganese ion. So let's do manganese first. So I'm going to use this Aufbau diagram here to show me which order the orbitals are filled in. So I'm going to follow this arrow down, so it shows me that 1s is first, so I'll check that off. And I know the s orbitals hold 2, so I put a 2 here. Then after that I follow the arrow down, it's 2s, and I know s's are 2. Then I go to 2p, and I know p's are 6. And then I go to 3s, and 3 is 2. So now I'm just checking. I have 4 and 6 is 10. I have 12. So, oops, we forgot to see what manganese. Manganese is 25 electrons. So I need 13 more places for electrons. So after 3s2, I go to 3p. So I'm going down this arrow. So 3p. So 3p I know is 6. So 6 and 6 is 12, 14, 16, 18. So I have 7 more electrons to go. So then I'm following my arrow down. Oh, look at this. After 3p is 4s. So I skip over here, and I know s has 2. And now I have 20 electrons, so I need 5 more. So I go after 4s. Look, I jump up here, and then I go 5 to 3d. So that will be my 5 electrons. And so this is the full electron configuration for manganese. Well, what about manganese ion? Well, you remember 2 plus means that I've lost 2 electrons. So I need to lose 2 electrons. Well, we know from studying ions that those electrons are lost from the valence electrons, and valence electrons are always the electrons that are at the highest, outermost quantum level. So I know I'm going to lose the 2 electrons in the 4s. So manganese ion is simply the same configuration as manganese, just minus 2 outer electrons. So it'll be 1s2, 2s2, 2p6, 3s2, 3p6, and then 3d5. So that's a full electron configuration. Now let's do the shortcut electron configuration. So if I look at, I'm going to do the electron configuration for cobalt. So let's find out where cobalt is. Here's cobalt right here. So let's do its full electron configuration first. So it's 27 electrons. So we're going to do 1s2, 2s2, 2p6, 3s2, 3p6, and then we know that we don't go to 3D next, but instead we go up to the 4th floor and we fill in our S room with 2, so that's 20. And now I go back and I put 7 electrons in D. So this is the electron configuration for cobalt. But I don't want cobalt, I want the cobalt ion. So I know I'm going to lose 2 electrons from my valence electrons. And remember, valence electrons are always those electrons that are the furthest out. And my furthest is 4, the quantum level. So I'm going to be taking these 2 out. So my electron configuration for cobalt 2 plus is going to be 1s2, 2s2, 2p6, 3s2, and 3p6, and 3d7. Now here's a really interesting thing. Well, this configuration right here, 1s2, 2s2, 2p6, 3s2, 3p6, is the same as the configuration for the noble gas that's one row above the row where my element is at, so cobalt. So this 1s2, 2s2, 2p6, 3s2, 3p6 is 18 electrons, and it is the same as argon. So I can actually write argon instead of these 18 electrons, and then write 3d7. And that is the condensed electron configuration for cobalt 2 plus. So we simply substitute this configuration, which is the same as the noble gas, of the noble gas that's a row above the element that I'm interested in. And then I have a shortcut or condensed configuration. So why don't you go ahead and try 5 problems. Do these in your interactive notebook. Problems 9 and 10 on page 14 and 4, 5, and 6 on page 15.